Conjugate roots theorem, example 3. We're given that z, 1 plus 2i, is a root of a cubic equation. We're asked to show that z bar, the conjugate of z, is also a root, and hence we're asked to find a third root. So we're solving a cubic equation. If z bar is a root, it means if we sub it into the equation, it will evaluate to be 0. So let us sub z bar, which is 1 minus 2i, into the equation instead of z. So we have our z cubed term, our z squared term, our z term, and the constant term. We're trying to figure out, does all this equal to 0 when we evaluate it? There's a little bit of work to be done on this. I'm going to do it fairly quickly here. The z cubed means z by z squared, so it's 1 minus 2i multiplied by z squared. And when you square a binomial, you square the first thing, that's 1 squared, multiply the two terms and double it, and square the last term. Then we're taking away from this, again the same thing, 1 minus 2i squared. So we've already done the work on that. It's 1 minus 4i plus 4i squared. And remember, I squared is negative 1. And then we multiply 3 by 1 and 3 by negative 2i, and we have 5. Now I notice we have a 1 times the z squared term, and we're taking away the z squared term. So these would cancel out. So that's just being a little bit clever. Then we have negative 2i by 1, negative 2i by negative 4i, negative 2i by negative 4. We have an 8 and a negative 6i. Adding these together, we end up with 0. So that tells us that 1 minus 2i is a root. Now, because we have two roots, we could get the quadratic factor from these roots. So using the rule that z squared minus the sum of the roots times z plus the product of the roots will be equal to 0, allows us to find the quadratic factor using the roots. So what we have is z squared minus the sum of the roots means 1 minus 2i and 1 plus 2i added together times z, and the product of the roots is 1 minus 2i multiplied by 1 plus 2i. Again, notice here we have the difference of two squares. We always get that in the product of conjugates. So we have z squared. When we evaluate here, we have a 2i minus 2i, which are cancelling out, and a 1 and a 1, which is 2. So it's negative 2 times z is what we get for negative the sum of the roots. And the product of the roots, we get 1 squared minus 2i to be squared, which ends up being 1 plus 4, which is 5. You could work this out slowly if you wish. I'm doing it quickly here. Now that we have a quadratic factor, we could find the missing linear factor by division. So if we divide our cubic equation by the quadratic, the way we normally solve cubic equations, we'd be able to find the missing linear factor. I'm going to use the array method for this division. We know where to place the z cubed term. Z multiplied by z squared gives us z cubed. We know where to place the constant term 5. 1 by 5 is 5. So we actually have our linear factor already, z plus 1. I'll multiply out the other parts to show it works. Z by negative 2z is negative 2z squared. Z by 5z. 1 by z squared. And 1 by negative 2z. We see the z squared terms add up to negative z squared, and the z terms to plus 3z. So we know that it's correct. So if the factor is z plus 1, well then we have the root is z is equal to negative 1. So we found the third root.